No, okay, let's start our seminar. Let's calculate some group cohomology. Ага.
А вы расскажете, вот как вот это вот через X определение будет связано через сингулярные гомологии пространственным первой или нет?
Ну вот сейчас более-менее скажу. Мы же в прошлый раз это вроде обсудили почти.
Не помню.
Ну в самом конце, когда там чуть не сходилось, но сейчас вот вроде как в конце сошло. Сейчас я это повторю. БЖ это есть Либерг-Маклейн.
Ну да.
Ну вот. The first, recall. Okay, no, recall algebraic definition, yes. We have, for any group G, we have group ring. G modulus is modulus over this ring. And homology of group in coefficient, with coefficients in some G module is by definition just store over this group ring between trivial module with trivial action and your module. And cohomology is X from trivial module to your module. No, previous time we checked that its derived functors of zero functor. Zero functor is just tensor product of trivial module, and this is just co-invariance. It's by definition m modulo g m minus m for any element m and for any element g of g. And cohomology zero is hom over g from trivial module to m. No, it's just invariance. It's such m, such that gm is m. This is zero functors, and this is their derived extensions. Okay. No, and what we can. No, okay. First observation is topological interpretation. If we have EG, it's contractible space. We have regular cover, the free action of G, and BG. Then, if G, because G is discrete, it's cover. So if it's contractible, this is space of KJ1. Yes, it has only one fundamental group, it's G, and all other groups are trivial because this is contractible. This is cover. So, and it's easy to prove that singular complex of EG as G module, it's free. No, as G module, each the thing is isomorphic to CNBG as Z module, extended. So it's free ZG module with basis of all singular simplexes of BG. It's modules. It's not true as chain complex. Yes, it was wrong the previous time. No, but each module is a free module. So okay, and so if we consider not just chain complex of such things. Augmented chain complex. We have augmentation. Now then, this is just a singular chain complex of space EG, contractible cover of BG. This is exact sequence because EG is contractible, and so EG is contractible means just that singular complex is also contractible, so it's acyclic. And each G module here is just free G module because it's free G module. Yes, so it's exact sequence of free G module, so it's free resolution of Z over ZG, and so we can compute homology of G in some module, as homology of this tensor product over G, and cohomology also. It's just cohomology of hom from CEG to M over G. It's so called in topology. It's called homology and cohomology of BG with local coefficients. Okay, but if so we have this resolution, we can consider tensor product or home to any model and obtain homology and homological group. But if M is trivial, G module, so action of G are identities on M, then we can consider, no, we can see that Cn EG tensor Gm is just isomorphic to Cn EG tensor G Z tensor Z M. This is because this is trivial. This is not true for non-trivial module, but for trivial module it's true. And this is this because from this identity we see that this is just CNBG. CNBG. So for trivial module we can see that, and in fact, yes, and in fact, well, this is true for chain complexes, that for trivial module you can check that this tensor product as chain complex with differential here and identity here is isomorphic as chain complex to CBG tensor with differential here. So this isomorphism of chain complexes of chain complexes of abelian groups. So we see that for M is trivial, we obtain that homology of Gm is homology of this chain complex. Now this is by definition ordinary singular homology of Bg with coefficient in this abelian group. This is Kg1 and homology also. No, and homology also you can check that home from this to M, if M is trivial, is home from C and Bg to M as abelian groups. So this is our topological interpretation. It follows from this, and from this easy check. So this is not true for non-trivial M, yes, because no, this is not true. Yes, this is not true. This is not isomorphism of chain complexes. Yes. But this is not isomorphism, not iso of chain complexes in general, for non-trivial M. Okay. For each n, it's isomorphism of abelian groups, but if not isomorphism of chain complex, it's important. It's also isomorphism of chain of because if you consider here G M, you can eliminate this. So as abelian groups is isomorphic in each degree, but there has different differentials, yes, in general. Okay. Because here differential is not just from this; it's kind of like I don't know how to say it. No, here differential here is not just differential here tensor with identity. It's not true. It has some mixing here with G action. Okay. Okay. But if M is trivial, then this tensor product kills this mixing, and we obtain only this part. So for M trivial, this is a morphogen complex, something like this. It's directly checked. You can check this from formulas. Okay. Okay. This was your question. For example, from this, we obtain some corollaries. For example, what's the BG? Okay. For example, what the first homology is coefficient in Z? No, it's first homology of BG. First homology of space is just abelianization of fundamental groups, and fundamental group of BG is by definition G. So this is the abelianization of G. And cohomology, it's always home from the first homology to Z. So it's home from abelianization to Z as abelian groups. No, it's the same thing as hom from G to Z. No, as not necessarily abelian groups, because any homomorphism from G quotes from to abelianization because Z is abelian. Okay, you can check this directly from definition. For example, because we can start do projective resolution for Z. We always have augmentation ZG epsilon, which sends any G to unit, and its kernel is augmentation ideal. It's free abelian groups generated by G minus H, or it's ideal generated by G minus 1. We discussed this the previous time, yes? Okay, and so if you want to compute this, for example, this thing, what is first homology? First homology is Tor between Z and Z over ZG, Z and Z. So you need if you for example, okay, if you consider long axis sequence for Tor for this, okay, in general, what?
What are we trying to prove?
I want to try what. Let's we have this short axis sequence of G modules. So if we consider long axis sequence for Tor, what we obtain? For any module even. I have that this is free module, yes. So all higher Tor or X with this is 0. So for example, for Tor, we obtain that. What I want to say that Tor n Zm isomorphic to Tor n minus 1 Egm. Yes. For what? No, maybe it's true for n started with 2, yes? No, because we have map, yes? We have.
This is from long axis.
Yes. It's Tor n minus 1 Zg m, and this is 0 for n greater than 2, and here is Tor n of this. Yes? So for n greater than 2, when it's 0, then it's 0. So we obtain isomorphism. Yes. It's general fact. And for so it's homology. Homology of G. It's always this Tor. And homology also. Homology isomorphic to X. With the same reason. In dimension 1, we obtain that what we obtain in dimension 1. We obtain that if n is 1, that first homology here is always also 0 because this is Tor n between Zg and m. So and then it's in injection to Tor 0. So it's something like this, and then it goes to Tor 0 between Zg m. So it's mg, something like this. So it's kernel of this map. And for example, if m is trivial, if m is z, if m is just z, what we obtain? Do you agree with this thing? It's Tor 0. It's Tor 1 between Z and M. It's Tor 0 between this and M. And this is Tor 0 between this and... sorry. Yes, this is just M. Wow. This is ZG tensor with M. It's our ring, okay? It's from this to this and this. This and this. This tensor product with ideal, tensor product with ZG by itself, but it's just M itself, okay? What? So the thing is always kernel of this map. The first, no, this is isomorphism. This is kernel. If M is trivial, Z, for example, what we obtain? No, this is Z, and this is no, yes, it's just GZ. It's kernel from no, in fact, maybe let's consider the next map. Next map, it goes to Z tensor GM. Whoa. And this is the end. And if M is trivial, no, this is coinvariance. This is factorization from M to coinvariance. It's always surjective. Maybe it's not injective. But if M is trivial, then this is bijection. Because if M is trivial, then this quotient is just M itself, okay? I just write down this non-trivial term of a long exact sequence, and this is the end of this long exact sequence. And if M is trivial, then this is isomorphism. Okay? Because this coinvariance is M modulo action of G. If it's trivial, then it's M itself. I have no quotient. All my quotient is 0. Because it is by definition M modulo GM minus M. If action is trivial, this is 0.
Yes, but the action on G is trivial. Isn't it true always?
Yes. No, this is definition. Z M tensor over G with Z is just coinvariance. Yes. So this is coinvariance of M. Okay. No, this is for any M. It's just for. Yes. If M is trivial, this arrow is isomorphism. Okay. Because in general, this arrow is just quotient from M to coinvariance. Okay. This is what epsilon tensor ID. It's quotient from M to coinvariance. Do you agree? If M is any. It's always quotient from M to coinvariance. But if M is trivial, this is just isomorphism because this quotient is isomorphism for trivial M. But for any M, this arrow is just quotient from M to coinvariance. For trivial M, it's isomorphism. So for trivial M, we obtain that this isomorphism, so this map goes to 0. So in fact, not 0. This means that this is epimorphism. So in fact, for trivial M, for Z, for example, we obtain this is kernel of this map.
Wait, so we obtain the first homology is 0 if M is trivial. I mean, because this is isomorphism, then IG.
No, this isomorphism means that that just image of this map is M itself. No, something like this.
Why?
No, sorry. Yes. Yeah, you're right. Yes, this is 0. Sorry. Yes, you're right. Yes. Whoa. If M is trivial, then this map is 0. Okay, goes to 0. Whoa. And this means that for trivial M, we obtain this is also isomorphism for n union 1. So if M is trivial, we obtain that this is it's also Tor 0 between EG and M. This is by definition EG tensor G M. Okay, so this is always true for n starting from 2, and for n is 1, it's true for trivial models. Okay, what we obtain. Do you agree? No, then this arrow is isomorphism. If this is 0, then this is isomorphism. Okay. It's injection and its image is kernel of this map. This map is 0, so it's surjective. And this exactly Tor 0, it's tensor product. So this formula holds for n equals 1 if M is trivial, okay? Now, in particular, you obtain that first homology with coefficient in Z is just coinvariance of EG itself. Coinvariance EG itself. Oh yes, you also know, and we can also maybe we we said this before also, that coinvariance, what is coinvariance? Coinvariance is Z tensor M, but it's also isomorphic to M modulo, no, augmentation ideal, yes? We also discussed this previously. No, it's more or less, no, because it's generated by G minus 1, it's the same thing. And so, no, what's the first homology is IG modulo IG squared. No, you can directly check that this thing is isomorphic to abilization of G. You can algebraically check this. It's just, so this we obtain algebraically. No, this is you can check directly. This is G modulo commutator. You can construct map in one direction and in opposite direction, which are inverse to each other. No, more or less, G goes to G minus 1. And modulo commutator, you obtain modulo square. You can check this. In fact, map G goes to G minus 1. Class. This is correct and this is bijection. You can check that this is isomorphism. It's from algebraic point of view. Of course, from topological, it's more or less, no, from topological, no, it's also some lemma that first homology is abilization of a fundamental group. It's some topological argument. It's some topological argument. In fact, okay. No, in homology, the same thing you can check. Okay. Now maybe, yes, I had another simple exercise that if your M is in fact RG module for some commutative ring R, then you can calculate homology and cohomology with Tor over Rg between R and M. No, and cohomology also. No, a simple corollary from this is just that if this is true, then in fact, for example, homology and cohomology also are modules. It's not just abelian groups, it's R modules if R is commutative. No, in fact, this formula holds. Did you do this?
What?
Did you do this exercise? Okay, then I leave it again. It's an exercise. No, it's easy exercise. No, so in corollary, then it's R modules if R is commutative. In general, for example, okay, maybe I say this further. Okay, now let's compute something. No, we compute first homology. Let's compute all homology for some groups. For example, no, cyclic groups. But if G is infinite cyclic group, what the ZG as a ring? What is the ring? Of course not. Z is just group. You have it's free abelian group with basis elements of Z. With multiplication that no, you have basis numbered with integer numbers with the following multiplication. What is this? No, maybe I need something like this for simplicity. What is this? Does this look familiar? This algebraic structure. If you have some elements and, no, for example, from this follows that, what is E?
Symmetric power?
No, it's not just, we have no binomial coefficients here. Symmetric power, no, symmetric, it's divided power, no, symmetric, no, it's, no, yes, it's kind of symmetric power of one-dimensional vector space. What is it? No, we have that En from this formula is just power of one generator. What does it mean? If you're ring and you have basis in each dimension, you have your, no, En is just power of E, of one element E. If I, okay, let me denoted by, for example, t or x.
Why is it not symmetric power?
No, it's symmetric power of what? No.
One-dimensional.
Yes. What is it? What is it? What is the ring? No. It's symmetric power, one-dimensional ring. What is the ring? It's
polynomial.
Yes, it's polynomials, of course. It's a polynomial in one variable. No, but it's not polynomial because we have even negative negative powers. Yes, it's Laurent polynomials. Yes. It's just Laurent polynomials. Okay. And so now let's try to write down free resolution for z. Now we have always augmentation, c plus minus 1. Here must be augmented ideal, but what the kernel of this map? This map sends t to unit. So no, because no, augmented ideal is ideal generated by g minus 1, but we have our group is generated by t, so it's ideal generated by t minus 1. But this thing is free one-dimensional module in our situation with this basis. So yes. So this is the end of our resolution. This is free module with this thing. Okay. So this is free resolution, and we, for example, obtain. No, what we obtain? We obtain that first. Okay, if we have some module. No, yes, maybe. Let me rewrite this. Consider this is one-dimensional module, and this map is multiplication by t minus 1. It's injection, so this is free resolution. So for any module we obtain, after we tensor with m, we obtain the same thing. It's for homology, and for cohomology is the same thing, but with opposite arrows. Yes. So we obtain the homology of z. This is group. This is comma with the dot. It's coefficients. What is it? No, it's 0. It's coinvariance. It's m modulo t minus 1. It's the same thing as coinvariance because we only have action of one generator, and if it's trivial, then all action is trivial. And the first, no, it's kernel of t of this map. It's it's invariance. Yes. It's invariance. Invariance. It's kernel of t minus 1 because it's such elements which are fixed by the action of t. So this is coinvariance, this is invariance, and all other 0. And cohomology, the opposite thing. 0 is invariance and 1 is coinvariance. Invariance, coinvariance, and 0. No, this is so-called Poincare duality because it's S1. It's a manifold, one-dimensional manifold, so we have duality between homology and homology. BG is S1, it's manifold. Okay. Okay, let's consider now finite cyclic group. This is, okay, yes, in fact, this thing have two generalizations. First generalization is finite cyclic, another generalization is free group, because it's also free group. Now we will consider free and cyclic. Now, for example, let's start with cyclic groups. If this is z modulo n, what is zg? Is a ring. We also have one generator, all other powers, but we have a relation. So it's just polynomials modulo tn minus 1. Because in n it's generator, and in nth power it's unit. So, oh yes, maybe okay. No, yes, let's start. Let's write down our free resolution. We have z. We have zt. It's epsilon. Kernel is it's always it's also yes, its kernel is ideal generated by t minus 1. It's ideal generated by t minus 1. What are the elements in our ring which are divided by t minus 1? What is it? No, I have this identity. Сейчас я даже, может быть, в общем случае скажу. Сейчас, секунду. And from the identity, you can check. No, and this is 0 in our ring. So, for example, it's easier consequence. If our thing is divided by t minus 1, then it's in kernel of multiplication by this element. This element is called norm. Norm of our group for any finite group is just sum of all elements. It's sum of all elements. Norm is sum of all elements of our group. It's element of group ring. It's defined for any finite group. No, and in this situation, you can check that this is equivalent, say. If it's in kernel of this map, then it's divided by t minus 1. So in fact, this kernel, we can consider this always also our ring, and this is multiplication. This is multiplication by t minus 1. It's always true. But kernel of this map, it's image of multiplication by norm. If it's vanished by multiplication by t minus 1, this means that it's obtained by multiplication by n, and vice versa. If it's kernel of n, then it's multiplication by t minus 1, and so on. And so on. No, it's infinite thing. It's infinite project resolution. But it's a periodic. T minus 1 and t minus 1 n. You can check that. No, you can directly check that this is exact sequence. That image of n is exactly kernel of t minus 1, and image of t minus 1 is kernel of n. That composition is 0, it is this equality. No, you can check that it's in fact exactness holds here. Okay, this is a cyclic resolution for cyclic group. No, periodic resolution for cyclic group. If you calculated sometimes chain homology of projective space, for example, projective space is Z2. No, this is it's also periodic. 0, 2, 0, 2. No, that's the same thing. Okay.
What are BG of Zn?
Of Zn? No, it's no, S infinity modulo Zn. It's so-called
length spaces.
Length space, infinity length space, yes. For n2, it's Rp infinity. Okay, and so if we tensor with m, we obtain the same thing with nm. So homology of our Zn is coefficient in m. It's no in zero dimension is always coinvariance, and then it's periodicity. If I is odd, then it's no kernel of t minus 1 is coinvariance modulo image modulo n m. N is some element. It's odd. And if m is I is even but not 0, then it's no kernel of multiplication of n modulo image of t minus 1. If I is even and greater than 0. Or something like this. No, in homology also the same thing, but with twist in this thing. No, it's invariance here, and these things are interchanged. It's also because some kind of duality, because no length space is manifold. It's direct limit of direct limit of manifolds. So we have periodicity here and duality also. For homology, we have this interchanged. No, and the coinvariance became invariance.
Length spaces are compact. No?
It's not. It's compact, of course, because it's it's not compact, but it's not. It's direct limit of compact manifolds. In each dimension, you have it's direct limit of compact manifolds because finite dimensional length space is compact. Mm-hmm. No, it's not formally, but yes.
Okay.
Okay, this is for cyclic group. Okay. Yes, and homology is the same thing. So this easy observation, easy resolution. Okay, another generalization of Z is free group on finite set of resolution. Okay, let's consider this situation. No, what from topological point of view, what the BG of this space, of this group? Of free group. What the Ellenberg-MacLane space of free group? It's a wedge of circles.
It makes sense.
Mm-hmm.
Yes, of course.
In general, classifying space of free product of two groups is wedge of classifying space. And so we know that from this point of view, we know, for example, at least for trivial modules, we have only 1 and 0 homology, and homology also. Now let's check that this is true for any module. What we know. Okay, let's start again. Z, G, epsilon, what? IG. And again, in general, this is free abelian group with basis G minus H. It's free abelian group. I claim that in the case of free group, this is free module over our ZG. Over our ZG. It's kind of exercise, but maybe we will discuss now. EG for free abelian group. It's let me denote it by F, okay, for shortness. It's free module with the basis. No, what do you think? What basis I need to consider? In general, for any group, it's just ideal generated by G minus 1. So of course it's generated by G minus 1. But here, if I want its free module, not just module generated by these elements, a free module with basis. What do you know? What do you think? What's the basis in this situation? It's set of generators, and what's the basis? No, what do you think?
Psi minus 1.
Yes. No, you can check this from this by induction on length of words, something like this. Now, for example, what if you have Jx minus 1 is just Jx minus 1 plus J minus 1, yes. And so here we have this thing with length something, and here is my basis element, G, and this is with length lower by 1. And so by induction of length of word, you can check that, that all these elements can be write down in these elements and vice versa. Now, for example, you know that, yes, something like this. Yes. It's an exercise. Okay. Is this правдоподобно?
Very правдоподобно.
Okay. Well, then try to check this. Okay. So it's free model, and so our resolution ends finished here. So yes, we obtain that corollary that homology of free group in n elements in any module. No, it's just coinvariance. No, some cohomology. No, some first homology. And no, okay. It's 0 for I greater than 1, and cohomology also 0 if I greater than 1.
So the claim is that for free, when the group is free, the mutation ideal is also free.
Yes, free model, and so this is end of our free resolution. And this is important quarterly, and this is important because in fact there exists a theorem of
zero is because distribution is free.
Yes, because by dimension reasons, of course. But a theorem of Swan and Stallings in fact say that if you have some group such that all cohomology for any module are 0 for I, then G is free. So in fact it's kind of characterization of free groups. But for any module, of course. Now here we observe that it's true. No, this is in fact true on exactly for free groups. No, yes, and in fact here it's not important that this is free group was finally generated. In fact, it's maybe it's could be some set of generators, and this is also basis. Okay, so in fact, no, this is free, not necessarily with finite set of generators. This is alpha. Okay, this is free groups. Now let's consider this observation. Let's try to compute homology and homology of free product of two groups in terms of homology and homology of terms. From topological point of view, we know this thing. So we obtain that for M is trivial, what the homology of free product? What is it? If we know this thing. Direct sum, yes. If I greater than 0. For 0, it's just M itself. It's coinvariance of trivial modes always M, because this is a connected space. It's always Z with coefficient Z, for example. Okay, now let's check that proposition that for non-trivial for any module this is true for I greater than 1. No, and for homology also this is the same thing. No, and exercise will be give an example where it's not true for I is equal to 1. It's not true for non-trivial module, for in general for.
Wait, what's the proposition?
No, that this is also direct sum, but for any module, not trivial. This is also for only for trivial modules, because homology coincides with homology from topological point of view for trivial modules. Proposition that is true for any module, for any M. It's a module over a free product. But because, no, maybe, yes, it's kind of functors, but no, I think it's more or less trivial because you have inclusions of your groups. And so if you have module over this, of course, it's modules over J and H. And here I consider this with restricted module structure, okay? And this is true starting from 2. And it's not true for I is equal to 1. You can consider, no, you can check some easy example of non-trivial module when it's not true. No, okay, why is true? No, again, our main observation. It's what the augmentation ideal of free product. It lies in this thing. No, yes. What do you know? What the free product? It's all words with GH elements from G, elements from H, or from HGG. Yes, and so this is ideal generated by difference of these words, and as ideal over this thing, it's generated by elements word -1. Yes, it's some word. Now, for example, if this word starts with G, so this means that this is G H -1. No, this is the same. It's the same calculation as before. H -1 plus G. No, sorry. Minus H plus H blah blah blah, the same thing, plus H blah blah minus 1. Well, just this equality. I just plus and minus H. No, the same word without J. And what does it mean? This means that what does it mean? No, of course, and now I need some inductive procedure. Okay, what I want to say that as module over this thing, as submodule, is equal to the following thing: IG tensor over G with ZH, GH. Direct sum is EH or H ZGH. Or as ZGH modules, for example, from the right. Something like this. Now, for example, what this thing.
When you write
this thing is equal to G -1 and word from which begins from H. G -1 lies in this thing, and this is words from this. So this part from this thing, and this part, in fact, from this thing, something like this. And so on. By induction, again, by induction on length of words, you can check that this is this thing.
Can you write Z, free Z of G, free product with H, and
No, where is Z?
no, I don't understand why we tensor with G. So we act with the elements from H trivially or what?
No. This is Z GH. This is our ring of our big group, and our small group it includes. Maybe we will discuss this on lecture today. No, we have inclusion of rings. So no, you can no. So this thing is module over these rings because it's subrings.
I see very stuff. Okay, I understand.
No, so if you like combinatorial group theory, you can easily check this thing. It's kind of in fact it's kind of generalization of the previous thing that it's free for free group, because for free group is free product of Z. You can check this for Z, and then by induction obtain the previous thing. It's kind of generalization of this thing. Okay. No, and from this, okay, of course we can now calculate easily this thing. For example, okay, let's start. Let's calculate homology. For example, I homology. If I is greater than 1, then by the previous our general fact is always isomorphic to Tor I minus 1 between augment ideal and M. It's why we need augment ideal here. It was general fact in the beginning of seminar, yes? Now then, this thing is direct sum of GH modules. So we have a direct sum of Tor. Let me, okay, for simplicity, write down only groups. So it's three modules. It's three modules of ZG. So no, again, it's yes. Again, claim that this is three modules with two summons. No, sorry, it's not maybe. Sorry, it's not maybe. It's not free. It's extended modules. It's modules with module structure from some abelian groups and tensor product. Okay. No. M plus the same thing for G, for H. And what is it? No, maybe I need to recall another general fact, maybe. Yes, because we will discuss it today on lectures, but let me recall. It's change of base thing. It's very important. If you have ring of homomorphism, for example, here it's okay. Ring homomorphism. No, for example, in our situation, for example, for inclusion H to G, it's ZH to ZG, for example. But if you have general ring homomorphism, then in fact you have three spectral sequences. No, in our situation we need the following spectral sequence: homological type with the second page of this form. And you have two modules. No, okay, now let me Tor P, Tor Q, S, M, N, and converges to Tor P plus Q, M, N. Here, M is R module. We consider S as R module. This thing is already S module, and this is S module. And we consider Tor over S. And here we consider Tor over R, where we forget S module structure on N. Is this obvious?
No, it's not, but we proved this.
No, we proved, yes. It follows from B complex. You consider P resolution for M over R. And Q is resolution for N over S. And then you consider S tensor. No, maybe here. No, if it's not commutative, maybe here it's something like this. No. You consider P tensor R S tensor S Q, or something like this. It's B complex, and two spectral sequences for this B complex. From the one spectral sequence you obtain second page, as usual. And from another spectral filtration from another spectral sequence you obtain the convergent term. This is just spectral sequence for this B complex. No, it's easy and important exercise for usual homological algebra. It's very easy and important. Okay. No, so in our easy situation, I want to say that what I want to say that okay, yes. In our situation, we consider, for example, what the first term. Consider ZG includes to ZG free with H. Now I claim that the thing, if we if we consider this as module over this ring, this module is free module over G. No, just with basis are words which starts not from G but from H. Something like this. We have basis G, H, and H. No, if it's G, then it's just I act on this word by G. So it's free module. It's free ZG module with basis H something. Okay? Because if I act on these elements by elements of G, I obtain any basis of all of this group. It can start with H, but also it can start with any other element of G.
So it must go H, G.
No, yes. But it starts with H. It's free left module. So in this situation, this module is free. In our situation, it's S. If S is free as R module, then all the store are 0 except of 0, 1. And so if S is free R module, no, then we just obtain that this store. No, so in this situation, for example, we obtain. No, okay. In this situation, we obtain that this store isomorphic to Tor over S M tensor S N. If S is free, because we obtain only 0Q, and in all our special sequence we have only one row, and then target is isomorphic to this row, as usual. Okay? Do you agree? Because in our spectral sequence, for any Q except of 0, this is 0 because S is free. So I have only one row in my spectral sequence, and then my infinite targets is in each diagonal I have only one element in this row, and this is isomorphic. And so no, in our situation, I obtain that this isomorphic to, it's our situation, we have extension, it's S, R is S over S. So I can consider, and I obtain exactly over R. So it's isomorphic to Tor I minus 1 over G, e.g. M. Where if I forget this thing. No, and this exactly Tor I minus 1 H, E H, M. And now, again, we know that this is isomorphic to.
You mean ZG that H is?
What? No. What? No, in our situation, S is M is Ij, and N is M. Okay? In our situation, this model is ideal. It's model of a G, it's smaller ring. This is M tensor over R, R is J, with S as big ring and another module here over big ring, Tor. Isomorphic to Tor over smaller ring, my smaller module, and this module. R is ZG, S is ZG free product with H, M is IJ, and N is M. Okay?
Yes, okay.
Where?
Tor ZG. Not here.
Where? Here?
Yes.
Where?
Tor, you wrote Tor H. I mean, H is not a ring, H is a group.
It's not a typo. It's my simplification of notation. I used it here already, and I say that let me write down only a group for simplicity. Okay? Yes, it is. And again, Tor I minus 1 is now isomorphic to homology as at this first isomorphic general thing. If I is greater than 1. That's all. Okay, so we see that this is true for any model in this range. No, this is not true for I equal to 1. Okay? It's an important thing. Now, of course, we know that from topological interpretation, we know that, for example, at least for trivial modules, we have QNet formula because for direct product of groups, it's isomorphic to direct product. It's just direct product of spaces. So, for example, for trivial modules, we, for example, have QNet formula. We have QNet formula and universal coefficient formula for trivial modules. No, because from topological point of view, homology of group is just homology of some space. So we have all topological things works here. And for example, we have multiplication homology. For example, in for trivial product, for example, GZ, we have cup product here, for example, because it's just homology of space. Something like this. Okay, from topological point of view, it's more or less trivial, but maybe one thing, for example, if, we have cup product here, but from another point of view, it's X over ZG between Z and Z, and here we have Yoneda product, if you remember this. If you interpret this X as classes of extensions of some length, then you have some extension and another extension. You can doing them together to one another. It's Yoneda multiplication on in each X for each X between for some model over any R. You have Yoneda multiplication. In this situation, this Yoneda multiplication in fact coincides with cup product. Huh? Coincides. We have one. We have maybe up to sign. We have one natural product in these things is the same things. Okay. Now let's now we construct some resolutions by your hands, but now let's consider our general resolution, bar resolution, for our group ring. Let me recall what bar resolution is. Bar resolution, if you have A is associative algebra with unit over some ring R, maybe. Then you have the following resolution. Differential works as we have no gradient, no differentials here, so any signs only from interchange. Okay, it's usual bar differential, okay? And if, and in fact I can, it's exact sequence of, for example, A modules from the right or from the left. We can consider A module structure from the right or from the left, from the leftist or from the rightest term. And also I can consider, I can consider A bar, it's A quotes by unit, something like this if it's, and then I can consider here bar, and this is also exact sequence. And now let me generalize. If n is a module, what? Может быть, только сейчас я подумаю. Значит, n, let it's right n module. Yes, it's right a module, and here we consider as right. Right или left? Сейчас я думаю, что у меня формулы потом сходились. Вот когда там стоят. Left. I think left. Yes. Left a module, and I can replace here the rightest one by n. And formula have the same thing, but I only have n on the last term. Maybe m, y, n. Okay, n.
Could you say some more words about a bar? I mean, how you insert a bar in the middle part? I mean, you spoke about it the last time, but
no, I have. If I have bar resolution, I have subcomplex of no, I think by trivial, is subcomplex generated when I have unit in some place in the middle term. And in fact, this subcomplex, this is contractible complex, this is also contractible complex, because our homotopy preserves the subcomplex. So the quotient, it's reduced bar. It's also acyclic. And this is quotient of this subcomplex. Okay. No, under some, okay, maybe under some assumption, no, this will be true for our group ring. Okay, for by definition, reduced bar is just this this quotient, and this is also acyclic. Why it coincides with if you replace middle term by a bar? No, it's true. For example, if a is free modulo and this is part of unit. Okay.
So middle term it means that every odd term.
Yeah, middle term it's in each term except of the leftist one and the rightist one. I have units here in all middle terms, maybe. And here I quote by any elements where I have even one unit in, for example. So, no, yes, what? So in bar resolution, if I, for example, have unit here, then it's 0. I have no units in my reduced term, in the middle terms. In middle terms of tensor products, not of complex. Yes, okay. Okay. And now, this is also exact sequence of left A modules. And now, if our, for example, our A is free R module, A is free R module, and if N is also free, no, yes, N is also free, of course, over our R. Then this is free resolution of A modules. Because as A modules, for example, this module, because it's a tensor over R, as A module, this is free with basis of this module over R, okay? If N is free product of R, then A tensor N is free sum of A. And the same. And again, if this is free R module, this free R module, this is also free R module, and then this free A module. So all these things are free R module, and then this is free A module with the same basis as this module has over R. This module has the same basis over A as this module has over R. Okay? Do you agree?
So this is a module like using tensor product?
Yes. We consider some R module, and this tensor product has A module structure from the leftist term. Yes, we consider the A module structure, left A module structure from the leftist term. And then if this is free, if A and N are free R module, then all the tensor products are free R modules, and this A module is also free with the same basis as this module has over R. Okay. No, and if A bar is also free, so for example, if unit is part of some basis of A, if unit is part of R basis of A, then A bar is also free, and then reduced bar construction, it's just this thing in this situation, and then this is also a free A module resolution of N. Okay. This is true, for example, in our situation. If R is Z and A is group ring, it's exactly a free module over Z. And unit is part of basis, so A bar is also free module. No, it's Z over G minus 1. It's free module over G not equal to 1. And so if we, in our situation, N is Z. We want construct free resolution for Z, and Z again free over itself. Z is free over itself. So in our situation, bar resolution works. Now let's write it down.
What do you mean resolution?
No, because I want free resolution. This is always resolution, but it's not maybe free. It's free only if A and N are free over R. But in our situation, A and R, and N is Z. A and N are free over R. And A bar also free over R, so we can use reduce bar resolution also. It's also free resolution. For example, it's always true over field, but in group situation it's true over Z, for example, because this thing is free over Z. And over any R, if I consider any R here, it's true over any R, commutative, because group ring is always free, so it works. If it's not free ring, it's not true in general, it's not free resolution. No, for example, over field, it's always true, over fields. But for group rings, it's true over any ring, okay? Because this thing is always, these things are always, no, free over R, by definition. Okay, let's write it down. What we consider Z as a left ZG module trivial. I have Z G tensor Z. No, I don't use Z. No, okay, I don't use Z. ZG, and so on. And what differential? I will consider each. Okay, let me. I will consider each term of this complex as free ZG module. It's free ZG module, left free ZG module. So I have, this is just my ring, and this is basis. So no, if I denoted something like, I don't know, B0, B1, B2, and so on, Bn is free ZG module, free with basis. No, it's kind of something like this. G1, Gn. Yes? I have n tensors. It's part of basis. In fact, part of all this G module is G0 also. But G0, it's, no, and this is basis. This is basis over ZG as left modulus, okay? Do you agree? And also, if I have reduced bar resolution, then then all these things are not equal to unit. Yes. I have this basis. And what the difference? In differential, if I have, I can write down differential only on basis, and on basis, that's the following formula. No, in fact, when I call that as a basis, as part of all bar resolution, it's kind of, I have unit here. Okay? Because no, if I have basis, and I have basic element from here, but as element from here, it's unit. It's just tensor with unit. So my differential, by previous formula, must just goes with this unit in this chart. So in fact, no, okay, I have the same thing. The same. Just one thing. No. No, not the same thing. Sorry. G. Во, вот так. Yes. It's my basic element of the previous bar term, and this is action of my G module. Something like this. And then minus G1, G2, Gn. Plus minus G1, Gn minus 1. And it's important that the final Gn disappears. Why it disappears? it disappears because it's action on z on the right. I don't write it down here, but it exists here. It's in fact it's z, and my last term is just j1 j n-1 n element of my module. But if it's unit, it's also unit, and I do not write down units here. I identify. In fact, here it's also tensor product with z over z, but I don't write it down. But then unit, I just don't write down unit. And so the final step is disappears. This is formula. Now this is important. If I do some simplification of notation. I just using only basic elements, and I do not write units on the right. And then this term disappears. For example, let's consider example.
Can you explain the first?
The first one, it's because this is unit in general, and in my usual bar resolution, the first term must be j1, j2, jn. But I consider this in Bn-1. In Bn-1, I consider this as term of basis, and this is action of my g1 as on basic elements. All other terms are basic, and the last term is also basic, but the last term disappears because it's action on unit on z. So I have this thing. For example, now let's compute again first homology, and again let's see that it's just stabilization of G. Let's compute first homology with bar resolution, for example. No, okay, sorry, yes. Now it's resolution, and now if I want to compute some homology of my thing with some module, I need consider some, now I think, right module. Okay, and tensor this resolution from the right by m and compute homologies. What does it mean? I have homologies of m tensor over G this bar resolution. Now let's write down differential in this situation. In this situation, I have m tensor. No, because it's free modules. When I tensor it with m, the first part exactly disappears. So I obtain m is 0. If I'm tensor this with m, it's again m over G. Okay. So and then it will be m zg, the first term, m zg, and so on. No, and formula, the same formula, in fact. No, where only the first term may be m. So differential of m tensor g1 gn, it's my n term, in fact, n term. It's mg1 minus and then plus minus, and again the last term disappears. One of the same formula. And now this is not exact chain complex, and it's homology of G. For example, consider trivial module Z. H, G, Z. It's homology of Z tensor my bar resolution. So in my bar resolution, I have Z, it's M itself. Then Z, G, and ZG squared. Okay. What's my differentials? I have G, it goes to, now it's just chain complex of abelian groups. So I need to compute my differential on abelian group basis. Now G goes to what? No, let's see. I have D1 tensor G. Now it goes to 1G, but my action is trivial, so it's unit. it's my augmentation. G goes to unit. What's here? G tensor, no, H. It goes to what? I consider it's as 1 GH because I have invisible Z on the left and on the right. I have two. In fact, for this complex, I have two invisible Z on the left and on the right. Okay, because it's in fact it's something like this. It's bar construction for Z, and I consider two tensor plots from the left and from the right and from the left. In fact. So, no, by my formula, I have again action G1. It's unit, so it's unit goes to unit G H. It's just unit, so it's H minus GH. It's okay. Yes, it's okay. Minus GH and plus G, where the final part is disappears. Whoa. Here, think. My G tensor H goes to H minus GH plus G. It's from the formula. Here I have two invisible Z, so my first disappears, last disappears, and in the middle I have a usual formula. Sorry. Okay, and so what's the answer? Answer is that the first homology is equal to new kernel of this map is augmentation ideal. So it's free abelian group generated by G minus 1. G minus H. Modular such things. Yes, this is. Just 1 second. It doesn't go to 0. It's not exact. It's not chain complex. Something's wrong. No, I have this thing. Yes, it's Z, ZG, ZG, and Z. I have unit, GH, and G. Sorry. Because I think that this is not epsilon. Because, no, yes. 1G goes to not, yes. Because I forgot here one term. It goes to 0. This is 0 map. Because 0 homology is coinvariant, it must be Z itself, not 0. Here, I forgot my last term, where here G does not disappear. It must disappear. It's G, it's unit, this thing, minus unit. It's 0. Because I have this thing, tensor 1. Here I have tensor 1, invisible tensor 1. I have this one minus this one. No, in each situation it's 0 it's 1 minus 1. So it's 0 in fact. This map is 0, sorry. This map is 0. No, because 0 homology is Z itself. It's not, in this situation it must be 0. So 0 homology is Z, it's coinvariant. So it's 0 map, sorry. And this map is this map. So in fact I obtain ZG itself. It's kernel of this map, yes. Modular this thing, GH is equal to H plus G. No, this is kind of abelianization. You have abelianization of not of group, but of group ring. In your group ring, you identify multiplication of group and formal sum. And because formal sum is commutative, it's also abelianization. And so from this it's not very hard to see that, in fact, no, you have formal sums of elements of G, but you do one thing, you identify multiplication of your group and formal sum. So in fact, all formal sums just elements of group is multiplication of elements. And they are commutative because formal sum is commutative. So in fact, it's abelianization of group. It's not very hard to see that it's just abelianization of group, okay? It's the, I think, fourth point of view on this first homology. Okay. Oh. No, it's important here, do not forget any terms, even trivial. because two trivial terms gives you some trivial but important thing that is 0. Okay, okay? Okay. Так, ну maybe it's time to do a break.